Welcome to qnawire.
To find the intervals where our function f of x is increasing or decreasing, the first thing we're going to have to do is find the derivative of this function. So we're just going to have to use the power rule to find this derivative. The derivative of x to the third is 3x squared minus 6x minus 9, and then our constant goes to 0. So this is the derivative of our function. And now the easiest way, in my opinion, to do this is to find the zeros of our derivative. So this is equal to 3 times x squared minus 2x minus 3, which is equal to 3 times, if we factor this, x plus 1 and x minus 3. And now we can figure out the zeros of our derivative because we have factored this, and they're going to be at negative 1 and 3. So f prime of x is equal to 0 at x is equal to negative 1 and 3. And now what we're going to do is look at the intervals where x is less than negative 1, where x is between negative 1 and 3, and where x is greater than 3. And we're going to see the sign. We're going to look at the sign of our derivative. So for x is less than negative 1, if we plug in a value, let's just say negative 2, negative 2 plus 1 is a negative value, and the negative 2 minus 3 is also negative. So we have a negative times a negative times a positive, which is positive. So this is greater than 0. And then from negative 1 to 3, if we pick a value of x is equal to 0, 0 plus 1 is 1, 0 minus 3 is negative 3. So we have a negative times a positive times a positive. So our derivative is negative in this interval. And then the last one is when x is greater than 3. Let's just pick 5. We have 5 plus 1 is 6 times 5 minus 3, which is 2. So these are all positive values. So again, our derivative is positive on this interval. And whenever our derivative is positive, that means our function is increasing. And whenever our derivative is negative, that means our function is decreasing. So we're increasing from negative infinity to negative 1, and from 3 to infinity, since we found that x values less than negative 1, we have positive derivative of f of x, and for x values greater than 3, we also have a positive value for our derivative of f of x. So that's where we're increasing. And then where we're decreasing is this interval from negative 1 to 3. So we're decreasing from negative 1 to 3. Now for part B, we want to figure out the local minimum and maximum values of our function f of x. And these occur when our derivative, f prime of x, is equal to 0. So what we're going to want to look at is the values of x is equal to negative 1 and to 3, since we found that f prime, this should be f prime, not f of x, is 0 at these points. And so what we're going to do is we're going to look at the actual data that we already found. So we're going to look at values of x that's less than negative 1. We see that our derivative is positive, and then values of x between negative 1 and 3 are negative. So we're going from positive to negative, which means we're going from an increasing slope to a decreasing slope, which means that at x is equal to negative 1, we have a local maximum. So if we plug this back into our original function, we'll see that f of negative 1 is equal to 9. So we have a local max at 9. And now for our other value at x is equal to 3. If we look at values that are between negative 1 and 3, that gives us negative values for our derivative of f of x. And if we look at values that are greater than 3, we get positive. So we're going from negative to positive, decreasing slope to increasing slope, which means that this is a local minimum. And if we plug this into our original function, we'll see that this is equal to negative 23. So we have a local maximum at the point negative 1, 9, and a local minimum at the point 3, negative 23. And now for part C, we're going to figure out the intervals in which our function is concave up or concave down, and then also where our inflection points are. So the way that we're going to do this is by finding the second derivative of our function, f double prime of x. And if we look at f prime of x again, in its original form, it was 3x squared minus 6x minus 9. So the derivative of that is going to be 6x minus 6. So our second derivative is equal to 6x minus 6. And now we want to figure out where this is equal to 0. So I'm just going to factor out a 6. We have 6 times x minus 1. So at x is equal to 1, our second derivative of x is equal to 0. So we know that there's this point at x is equal to 1 where our second derivative is equal to 0. And wherever our second derivative is negative, our function is going to be concave down, and wherever our second derivative is positive, our function is going to be concave up. So what we want to do is look at values of x that are less than 0 and see what the sign of our second derivative of x is. So if we plug in a value, let's just say of negative 1, we have negative 1 minus 1, which is negative 2, times 6, which is a negative value. So these are going to be values that are less than 0. And if we look at x values that are greater than 0, let's just plug in 1. Sorry, I should not have been looking at x is less than 0 and x is greater. This should be x is less than 1 and x is greater than 1. So if we plugged in a value of 0, we would have negative 1 times 6, which is still negative. So yes, we do have our second derivative being less than 0 when x is less than 1. And when x is greater than 1, if we plug in a value, let's just say of 2, we have 2 minus 1, which is 1 times 6 is 6, which is positive. So our second derivative of f of x is positive when x is greater than 1. So this means that we are concave down on the interval from negative infinity to 1, since for values of x less than 1, our second derivative, f double prime of x, is less than 0, and we're concave up on the interval from 1 to infinity, since our second derivative is positive on this interval. And now, lastly, the inflection point. These points are where we go from concave up to concave down, or from concave down to concave up. So whenever we have a change in concavity, we have an inflection point. And these occur when our second derivative is equal to 0 and we have a sign change. So if we were to look at the graph of our second derivative, f double prime of x, we would need a 0 that actually crosses the x-axis. We couldn't have a 0 that just touches and then goes back like this, since that doesn't have a sign change, which means we are going from concave. In this case, we're going from negative to negative, so we're going from concave down to concave down, which isn't a change in concavity, which means it isn't an inflection point. So we know that from finding values on these intervals that at x is equal to values that are less than 1, our derivative is negative, and x is equal to values that are greater than 1, our derivative is positive. So we do have a sign change at x is equal to 1, which means that our inflection point is at x is equal to 1. And that's our only inflection point.